All right, class, we're going to be going over some periodic trends. So kind of go over the structure of the periodic table and why it's organized that way. We've talked about it a little bit with electron configuration, but there's also some other cool things that we can pull from the structure of the periodic table. So let's open up the PowerPoint here. Awesome. Okay, so getting started here. Let's go ahead and pause the video and try and work out the electron configuration for an iron atom. Okay. All right, hopefully you paused that and got this figured out. So this is information from the last lecture when we talked about electron configurations. So if we look at the periodic table, and a periodic table like this will be allowed, or will be given to you on the exam. If you go to the content section on Learning Suite and then go to exam info, there's some sheets that you'll be allowed to use on the exam. So if you're ever wondering what will be available to you on the exam as far as like equations go or conversions, the information's on there. So all right, so let's look at the iron, right? So if we draw this whole thing out, right, we'll start with the 1s, okay? If we go through hydrogen and helium, right, I always just kind of start at the top of the periodic table and work my way down. So after that, we move over to the 2s, and then we go to 2p right here. Okay, and then we hit 3s, and then we hit 3p, and then we hit 4s, and then we hit the 3d. Okay, cool. And then iron has a total electron count of 26 because it's got 26 protons. It's 26 on the periodic table. So we'll count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. All right. So if we look at this electron configuration, right, we have 6 electrons in the 3d orbital here. So we could write this out as an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? But then if we're doing the shorthand for the noble gas shorthand electron configuration, if you look at this, this is going to be this exact same electron configuration as argon, okay? So this can be replaced with argon in brackets. Okay, so we should just have argon and then 4s 3d6. So we should get C. Awesome. Okay. And let's try another one of these. So go ahead and pause it and try this for the chromium. All right, coming back here. So if we look at chromium, sorry, this is the iron slide. I forgot to put the periodic table on the next one, but chromium is right here. Okay, so it's number 24. So we should have, the same orbitals available as we did with iron, but we just have 2 less electrons. Okay, so the answer here is E. And let's go ahead and go through this. So again, I said we were going to have the same orbitals as iron, right? So we go up to the 3d orbitals. With iron, we had 6 in the 3d. So with chromium, if we take away 2 electrons, we would expect to see 4 electrons in the 3d, right? That's 2 less than we had with iron. But we talked about 2 exceptions that we have. one of them being chromium, where this electron will actually jump up to this higher orbital, and it will look like this. And it just turns out that half-filled orbitals all across here is actually more stable than a fully filled 4s orbital with a partially filled 3D sublevel. So there's just the two exceptions to that. So looking at the periodic table, we have chromium and we have copper. Okay, those are the two exceptions where you have an electron move up from the 4s sublevel to the 3D sublevel. So just keep those in mind. Okay. All right. Yeah, so what the PowerPoint is showing right here is there's actually more than two exceptions. It kind of goes all the way down the periodic table. For example, all the ones under chromium would have a similar effect, but I'm not going to ask you about those. Just know the the chromium and the copper exceptions is all that I really care about. Okay. All right, so now we're going to be talking about valence electrons. Okay, so valence electrons is the number of electrons, or I guess valence electrons are the electrons in the outermost shell. Okay, so it's going to be the electrons in the outermost energy level is what we would consider a valence electron. So hydrogen only has access to the first energy level, right? So the first energy level with an S sublevel. So the first energy level only holds 2 electrons, right? That's the possible amount that it can hold. And so hydrogen, if you look at the electron configuration for hydrogen, right, it's going to have 1 electron in the 1s orbital. And since hydrogen is in the first row here, it only has access to the first energy sublevel. And so this electron that's in the 1s is actually the valence electron for hydrogen. So hydrogen has 1 valence electron. So all down the columns here, they're going to have the same number of valence electrons. So all of them in the first column, okay, are going to have, or a group, if you want to use that term, are going to have 1 valence electron. And then in the second group, or second column, you're going to have 2 valence electrons. And then in the third group, you're going to have 3 valence electrons. So this is a little confusing here. So this has a 13, and then it says 3a. So if you look at a periodic table, right here is actually where you'll see all of the D block elements, right, or those transition metals. So this is a kind of a stitched together periodic table. So if you skip over those D ones, this is called the 3a group because they all have 3 valence electrons. But technically it's actually the 13th group along the periodic table when you look at it. But the reason that boron, for example, has 3 valence electrons is because boron has access to the second energy level, right? So the second energy level includes the S and the P sublevels. And boron has 2 electrons in the S sublevel and 1 electron in the P sublevel. So it has a total of 3 electrons in the second energy level. And since the second energy level for boron is the outermost energy level, then this actually contains 3 valence electrons. Okay. Same logic applies for carbon. Has 4 valence electrons, nitrogen 5, oxygen 6, fluorine 7, and neon 8. And that same logic applies really for all these down here. Okay. All right, cool. So for example, just picking one randomly here, if you looked at the electron configuration for phosphorus, okay, you're actually going to have, let's look at like selenium, okay? So for selenium, if you drew out the electron configuration, the last part of the electron configuration, I won't draw the first part, okay? But the last part is going to be 4s, and you're going to have 2 electrons in it. 3d with 10 electrons in it. And then you're going to have the 4p, and it's going to have 4 electrons in it. Okay, so the outermost energy level, or I guess the highest energy level for selenium is the 4th energy level, right? So in order to calculate the number of valence electrons for selenium, we need to know how many electrons are in the 4th energy level. So we have 2 here that in the 4s, and then we have 4 from the 4p. So it gives us a total of 6 valence electrons, and that's why it's in the 6a group, okay? Same number of valence electrons as oxygen. The 3d electrons don't count because they're not in the 4th energy level. Even though they're kind of between these four, between the 4s and the 4p, right? They're still in the 3rd energy level, so they don't count for valence electrons. Anyway, okay. When you are asked a question about valence electrons, likely you're not going to be drawing out electron configurations. You're just going to look at the number at the top of the group, say, oh, it's in 4a, so it's going to have 4 valence electrons. And that's kind of how the best way to answer those questions. But the reasoning behind it falls in the electron configurations that we learned. Okay. All right. Okay, moving forward. Okay, so Lewis dot structures. We're going to talk about these more when we talk about like covalent compounds, and we'll talk about compounds and how to draw those Lewis dot structures for the compounds. But just as kind of an introduction here, you'll see these Lewis dot structures sometimes, and just remember that they don't follow the same rules as orbital diagrams. And what I mean by that is, like, for example, with carbon, okay? If you look at the orbital diagram, which is, I've sometimes referred to it as like the electron configuration diagram. Okay, so for carbon, you're going to have 1s, 2s, 2p, okay? And then it has a total of 6 electrons, okay? So carbon has 4 valence electrons. So what Lewis structures show are how many valence electrons are around it. If you look at the orbital diagram or the electron configuration diagram for carbon, and we look at just the valence electrons, which are the electrons in the 2nd energy level, you have 2 that are paired and 2 that are unpaired. So you might be tempted to draw a Lewis dot structure for carbon like this, okay, with like 2 paired electrons up here, and then 1 single electron to the right and 1 single electron to the left. But that's not how you draw them. When you draw Lewis dot structures, you first put all the electrons as far apart as possible. And then if you have extra ones, then you can start adding them next to each other. So that's what you see with nitrogen here, okay? So just because, don't get confused in thinking about the electron diagrams or the orbital diagrams and trying to draw a Lewis structure from that. To draw a Lewis structure, all you need to know is how many valence electrons, okay? So for carbon, there's 4, and then you'll just draw the 4 electrons around carbon, separated as far as possible. If there's 6 valence electrons, so if you're doing this for oxygen, you're going to draw 6 valence electrons, so you'll do the 4 first as far as possible, and then since you don't have another choice, you're going to start adding them next to each other, and that's where you get like what you see for the Lewis dot structure for oxygen, okay? And then this uses beryllium as an example. Beryllium's orbital diagram looks like this, but when you draw the Lewis structure, they're actually separate, right? So we kind of talked about that. Awesome. Okay. So now we're going to talk about properties of different sections of the periodic table. So the first one's the noble gases, which is the most far right group, or the 18th column or the 8A column, right? So these have, in general, they have 8 valence electrons, the one exception being helium in the top right corner, because helium is only in the 1st energy level, it can only have 2 valence electrons, so that's what it has, but the rest of them have 8. So, okay. So these are gases, which you probably knew because the name is noble gases. and chemically inert. And what this means is they don't really react with anything. Okay, so the reason for that is when you talk about reactions, you'll see it in like Chem 285. Reactions happen because of electrons moving. Okay, and so atoms that don't have 8 valence electrons are either going to want to gain an electron or lose an electron to try and get to 8 valence electrons, a stable, because that's the more stable electron configuration. So noble gases are already in the stable electron configuration because they have 8 valence electrons. So they don't want to gain or lose electrons, so they're not going to react with anything very much. Okay. So again, they're completely filled, right? Because they have their sublevels filled, their S and their P levels are filled, and so they have a stable electron configuration. Okay. All right, so halogens, those are the ones in the 7th or 17th group, and they have 7 valence electrons. They're generally found as diatomic molecules. Okay, so if you say you have fluorine, it doesn't mean you wouldn't just write F. Okay, so if you're like writing out a chemical reaction or something and the question says fluorine or chlorine, it's going to mean for fluorine it would be F2, or for chlorine it's Cl2, right? You never just put fluorine on its own, okay? So these form negative ions. So again, I talked about how atoms want to have a stable electron configuration, which means they want to have 8 valence electrons. So if we look at fluorine right here, okay, fluorine has seven valence electrons. So in order to be like the noble gases and have 8 valence electrons, it needs to gain an electron. Okay, so we need to add an electron onto fluorine. If we add an electron to fluorine, then it has 8 valence electrons, and it's happier like a noble gas. And when you add an electron, you're adding a negative charge. So by forming an ion, right? An ion is an example of if you have an atom and you either add or subtract electrons, you're forming ions. Okay, so when an atom has a charge on it, it would be an ion. So here, if we add an electron to fluorine, so that has a noble gas electron configuration, we're going to be giving it a negative charge because we're adding electron, which has a negative charge. Okay, and these ones are reactive because they don't have initially on their own, right? They don't have 8 valence electrons, so they're going to want to react. They're going to want to pull an electron from something else in order to get their 8 valence electrons. Okay, so you can see here acquiring 1 electron gives them a stable electron configuration. So for all of these that we're going to talk about, just think that you want to have a stable electron configuration, which means you want to be like a noble gas. You want to have 8 valence electrons. So whatever it takes to get there is what's going to happen for these atoms. Okay, alkali metals would be in the first group. Okay, so for those we have hydrogen, although hydrogen isn't really at room temperature, hydrogen is a gas, right? But anyway, it's in the first group because it has 1 valence electron. So hydrogen, lithium, sodium, and potassium are all considered in this alkali metals. Okay, so they're very soft. You can just cut them with a knife. Generally, we do like a demo where we put these metals in water and they react so fast that they cause like it catches on fire basically. And you could watch some YouTube videos on that if you're interested. Okay, so these ones form positive ions. So this is the same reason as why halogens form negative ions. We can use the same reasoning to see why these form positive ions. Okay, so for sodium, for example, this is showing 1 valence electron, right? And lithium shows 1 valence electron as well. So if we looked at the electron diagram for lithium, for example, we would find 1s and 2, actually, yeah, and 2s. let's look at sodium. I think it's going to be easier to see. Okay, so for sodium, we would have a 1s, a 2s, a 2p, and a 3s. Okay, and we'd have, so let me draw all the electrons in. Okay, 1 electron in the 3s. Okay, and since sodium in this electron configuration goes all the way to 3, right? The 3 is the outermost energy level. So it only has 1 valence electron. But if you pull this electron out, okay, if something takes that electron out, then you lose this orbital. And now you're considered that, you can just think that you're in the second energy level, okay? So if that's the case, you have 8 valence electrons, right? Because 2 is your valence shell. So now you have the same electron configuration as neon. So by pulling out an electron, you have a stable electron configuration like a noble gas, okay? So if you pull out an electron, you're pulling out a negative charge, it's going to make the atom positive when you do that, okay? And these are very reactive because they really want to lose an electron to provide a stable noble gas configuration, okay? Cool. And then following the same reasoning for alkaline earth metals, they're going to want to actually lose 2 electrons to get to that stable noble gas electron configuration, okay? And so when these ones form ions, they actually form 2+ charges, right? Because they're losing 2 electrons when they turn into a noble gas electron configuration. And then putting these in water and reacting them, they're generally less reactive than the ones in group 1A, okay? So again, losing 2 electrons gives the stable noble gas configuration on this one. All right. Okay. So go ahead and try this quiz question. Pause the video and see how you do. This is going to come from the reading if you did the reading before class. All right, let's go through this. So fluorine is the smallest, okay? And we're going to talk about why that is and some of the trends on size in the periodic table. So atomic size, you can see that the atoms get smaller as you move to the right and smaller as you go up, okay? So to the right and up give you the smaller atoms. So helium would be the smallest one, okay? And then obviously the opposite way gives you the larger ones. So you have the biggest one down here on the bottom left, okay? So just kind of memorize that trend. Pretty easy one to memorize, but we're gonna talk about why that is coming up right here. So size decreases across the period, okay? So remember, periods are the rows, okay? So across a row, the size is going to decrease, okay? So if we look at, let's just look at like the second row here. So as we move to the right, you can see the atoms are decreasing in size. So you're in the same energy level, okay? So you can imagine the electrons being, if you think of like, I'm doing it with my hands, but I realize you're probably watching the PowerPoint. So let's say you have like the nucleus of an atom right here, and you've all seen this model, okay? So this would be like your first energy level, and then you have your second energy level, okay? So you have all your electrons floating around in your second energy level, okay? So that's what would be the case with all of these in the second row. They all are in the second energy level, okay? So the number of protons in the nucleus is going to increase as you move to the right, right? Since they are increasing, it's going to have a stronger pull on the electrons that are on the outermost shell. And so as it pulls those electrons in tighter because it has more positive charge, it's going to make it smaller, okay? And so that's the reason that the atoms get smaller as you move to the right. And then up and down on a group, okay? Let's look at just the first group as an example here. Okay, so we have electrons in higher energy levels, so larger orbitals. So if you look at the diagram I drew, right, the first energy level's here, second's here, you'd have a third energy level here, right? So as you move down a group, you actually move through energy levels. And as you do that, the atom keeps getting bigger and bigger as you go. We saw in the last lecture that the orbital sizes increase as you move up in energy levels. So that would be why it increases going down. Okay. And then looking at ions, okay, so we have cations, which is a new term. Okay. Cations are positively charged ions. The way you remember this is you have a T in here, and a T looks like a positive sign, right? So cations are positive ions. Okay, and then they're smaller than the original atoms. So here, like lithium and beryllium, right? These form cations. We talked about how lithium will lose one electron to form a lithium plus. Okay, so lithium plus is a cation. Okay. So as you remove electrons to reach that noble gas configuration, remember as you remove the electron, you actually move down in energy level. Okay. So the valence electrons are one energy level lower, so there's nothing. For example, we talked about sodium, right? So if sodium loses an electron, sodium as it sits right here has electrons in the third energy level. If you remove that electron out of the third energy level, now you only have electrons in the second energy level. So the size decreases because you're only going out to the second energy level now instead of the third one, okay? And then anions are larger than the original atom. So anions would be, we talked about like halogens, right? So fluorine will actually gain an electron in order to achieve a noble gas configuration, right? And so as you get more electrons in the outer shell, they're going to kind of push away from each other. And as they push away from each other, it's going to be bigger because they're all negatively charged. They're going to repel each other. And that's why it gets bigger for anions. Okay. All right. Let's do a quick quiz. See how we're doing here so far. All right. So the question is, which of the following atoms requires the most energy when removing an electron? Okay. So this is going to be a term that we're going to start talking about called ionization energy. And at this point in the slide, if you haven't done the reading, you probably may not know what this is, but we're going to talk about it. So ionization energy is the amount of energy it takes to remove an electron from something, okay? All right, so you can kind of think of these. Some of these would be easier to think about than others. Lithium, for example, we know it wants to lose an electron because it wants to be positively charged. It wants to be like the noble gases with their electron configurations. Potassium as well, okay? But as you get down to some of these, like fluorine and bromine, they're both halogens, right? They actually both want to gain an electron. So that means it's going to be hard to remove an electron from something that wants to gain an electron in the first place. So I would say it's between these two for me, just looking at it, but that difference is going to be hard to know until we talk about why it is. But it turns out for this one, the answer is fluorine, okay? So again, ionization energy is the energy it takes to remove one valence electron from an atom. And then this little chart here, let's see, really helps us see the trends, okay? So in the first row, we have hydrogen and helium, okay? Hydrogen is going to be a lot easier to pull an electron from, right? Because it only has one valence electron, okay? And then as we move to the right, we can see that the ionization energy increases, right? Helium is a noble gas. It doesn't want to give up any electrons, so it's going to be hard to pull from that. All right, lithium is way easier to pull an electron from. Okay, it really wants to lose its electron to achieve a noble gas configuration, right? And beryllium is going to be a little harder because you need to pull off 2 electrons in order to do it. Okay. And you can kind of walk through these and see how they do, right? But generally, as you move to the right across the periodic table, the ionization energy increases. And then as you move down, the ionization energy decreases, okay? All right. Increases across the period to the right, decreases down a group, okay? All right, we'll talk about why for some of these. So increasing across a period, you have electrons in the same energy level, right? So we'd be talking about, like, if we're looking at the second period, it's this lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so that would be like moving right across the second period. So number of protons in the nucleus is increasing as we do this, right? So stronger pull on the electrons, we kind of talked about this. We talked about it in terms of making it smaller because the nucleus is getting more protons, it's going to pull the electrons in tighter, right? So since it's pulling on those electrons tighter, it's going to be harder for it to lose an electron, right? And so since it's hard to lose an electron, the energy to do that is going to be higher. So the ionization energy goes up as you move to the right. And then going down, so if we looked at like the halogens, for example, you can see that as we move down, that the ionization energy decreases. And so this is going to be, again, if we use that model, here's your nucleus, first energy level, second energy level, third energy level, right? So as you move down a group, you move up in energy levels. So fluorine only has access to the second energy level. And then as you move down, for example, if you go down to like bromine or iodine, okay, so well, let's just move to chlorine. Okay, so chlorine has access to the third energy level. It's easier to pull off an electron that's in a third energy level because it's further away from the positive charge of the nucleus. So chlorine is going to have a smaller ionization energy because it's easier to pull off this electron than it is to pull off an electron in the second energy level like fluorine has. Okay. Awesome. All right, so you'll notice like two funny spots on here where we say as you move to the right, the ionization energy increases. Well, that's true for the most part, but like from beryllium to boron, it actually decreases. And from nitrogen to oxygen, it decreases as well, okay? So if we look at the electron configurations for these, we can see why it happens. So for boron, for example, this is the electron configuration diagram or orbital diagram for boron, okay? And it just has one electron in the p sublevel. Well, it doesn't take much energy to pull this one out because if we pull it out, we still have a fully filled s orbital. Versus beryllium, for example, only has 2 electrons in the s. And so to pull this out and make it a half-filled s orbital is actually more difficult to do than to pull this one out of the p orbital, basically. Same thing with nitrogen to oxygen. So oxygen looks like this, okay? And so a half-filled orbital is more stable than a partially filled orbital. So to pull this one out and make it, half-filled sublevel is more stable than the partially filled sublevels. So if you pull out this electron, then you actually have a half-filled sublevel, which is more stable. So the energy to do that isn't as high. So that's kind of the discrepancy here between nitrogen, oxygen, and beryllium and boron that you see. Okay. So you'll just remember going to the right increases ionization energy, except between those two spots. Okay. And the last thing we'll talk about in this lecture, just kind of talking about some of the properties here. So in the last lecture, we talked about the divide, right? On the left side of the periodic table, you have metals, and on the right side, you have non-metals. So metals are going to have a smaller ionization energy because they want to lose electrons in the first place, so it doesn't take much to pull them off. And because of that, they form cations. And they're also good conductors, which probably already knew. And then nonmetals are the opposite, right? Higher ionization energy because they will actually want to gain electrons. And so because they're gaining electrons, they form anions, and they're poor conductors as well. Okay. All right. So I think that's it for that PowerPoint. Go ahead and study that, and just kind of like, mostly in general, you need to know those trends. Example of like a test question with that stuff on it would be like a list of 4 elements, and it would say which has the highest ionization energy, or which one of these atoms is the smallest, which one of these atoms is the largest, stuff like that. So you just need to know how to compare between elements in like the same row or the same period. I wouldn't ask you to guess like about two elements that are in totally random spots on the periodic table, because we just learned trends across periods and groups. So I would ask you about which is the smaller of these elements, and they would all be elements in the same group or in the same period or something like that. So awesome. Yep, practice that in your homework, and we'll see you next time.